For more information, please visit SGMAK Associates website.
Conditional probability of event B conditioned on occurrence of event A is expressed as probability B given A. Similarly, probability of A given B represents the probability of event A given that event B has occurred. So in estimating conditional probability, we work with a reduced sample space. Let's look at an example. We have a sample of 10 units and that has 2 defective units. 2 items are drawn randomly. We define event A as the first item is good and event B, the second item drawn, is good. Probability of event A is given by 8/10 because we have 8 good units out of a sample size of 10. Now if the second item is selected without replacing the first item, then probability B given A is 7/9 because we have taken already 1 unit out of the sample. Otherwise, probability B given A is 8/10. Let's look at another example. A pair of fair dice is tossed. X1 and X2 represent the number shown on the first dice and X2 the number shown on the second dice. So we define an event A as all collection of X1 and X2 where X1 plus X2 is less equal 5 and define event B as all collection of X1 and X2 where X1 equal X2. So moving on, the sample space has 36 outcomes. Probability of event A is 10/36 and probability of event B is 6/36. However, if we condition B on occurrence of A, then probability B given A is 2/10 because we have only 2 outcomes, 1, 1 and 2, 2 of the reduced sample space conforming to event B. Probability of A given B is 2/6, outcomes 1, 1 and 2, 2 of the reduced sample space 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6 are to be counted in this case. Probability of A intersection of B, same as probability of B intersection of A, which represents probability of simultaneous occurrence of both A and B. In this case, it's 2/36 because you have only 2 outcomes out of 36 outcomes in the sample space that satisfy both events. Without formal introduction, we can verify that probability of A intersection B is probability of A multiplied by probability B given A, and probability of B intersection A is probability of B multiplied by probability of A given B has occurred. Let's look at another example. An OEM has 3 suppliers for a specific part. The volume contribution and the defect rate from individual suppliers are as follows. Supplier 1 supplies 20% of the volume and has a defect rate of 5%. Supplier 2 supplies the bulk of the volume, 60%, has a defect rate of 3%. And supplier 3 supplies 20% of volume with a defect rate of 4%. Parts from different suppliers are mixed thoroughly. Now we select a part randomly from the mix and inspect, and we find the part to be defective. So question is, what is the probability that it is supplied by a specific supplier? Having found a randomly drawn part to be defective, what is the probability it is supplied by a specific supplier? We can solve this problem without formally using the Bayes theorem. Now we introduce Bayes theorem later in. Let us use 100 parts as the base of our computation. So quantity of defect, quantity of defective. Supplier 1, out of 100 parts, 20 are coming from supplier 1 and it has 1 defective. Supplier 2 is supplying 60 with an average of 1.8 defective, and supplier 3 is supplying 20 out of the 100 units and has 0.8 units defective. Now we can estimate the required probability for different suppliers from a kind of a conservation principle. Now, probability given the part is defective, it is coming from supplier 1, we simply have 1 divided by total number of possible defectives. So 1 divided by 1 plus 1.8 plus 0.8, 0.278. So 27.8%. Probability given the part is defective, it is from supplier 2, using the same computation, same reasoning, as 0.5, and probability the part is defective, given the part is defective, it's from supplier 3, is 0.222. So 27.8% is the probability or the chance that having found the part defective is from supplier 1. Now please pay attention to the difference between probability given the part is defective is from supplier 1, which is 0.278, and probability given the part is from supplier 1, it is defective, which is 0.05. The first element represents a weighted average of contribution of individual supplier to the pool of defectives. The second element simply represents the defect rate of individual suppliers. Total probability of an event A, you can write as probability of A is probability of A intersection B plus probability of A intersection B complement. It indicates that an event can happen with another event B and its complement. So it can be written as probability of A as equal probability of A intersection B plus probability of A intersection B complement, which equals to, if we use the conditional probability relationship, equals probability of B multiplied by probability of A given B has occurred plus probability of B complement multiplied by probability of event A given that B complement has occurred. Two events A and B are independent if and only if probability of A intersection B equals probability of A multiplied by probability of B. Now we can say, based on all your definitions, that if A and B are independent events, then probability of A given B has occurred is probability of A. Similarly, probability of B given A has occurred is probability of B. That indicates the events are independent. There are many instances where independence of two events cannot be established easily. There are many instances where such independence can either be justified or approximated from physical review of the process. The following example serves as an illustration. Let's look at this example. Suppose a random sample of size 2 is drawn from a lot of size 150 with 5 known defective items. The sampling is done with replacement. Let event A indicates the first item retrieved is good, and event B indicates the second item retrieved is good. The probability that both items are good, probability of A intersection B, is probability of A multiplied by probability of B, which equals 0.9344, assuming they are independent. Now without replacement, probability of A intersection B is probability of A multiplied by probability of B given A, which happens in this case 145 over 150 multiplied by 144 over 149, equals 0.9335, and the results are very close. The common practice is to assume events independent when the sampling fraction, sampling size versus population size, is small. A partition of the sample space may be defined as follows. If C1, C2, C sub k are disjoint subset of the sample space S, and if C1 union C2 union C3 through union of C sub k equals S, then the subsets are said to form a partition of the sample space S. If you have a partition, then only one of the events, C sub I, can occur. In turn, if k events from a partition, if k event C sub I from a partition A is an arbitrary event with respect to S, then we may write A as A intersection C1 union A intersection C2 through union A intersection C sub k, because only one of the C sub I can happen because they are the partitions of the sample space. So probability of A is probability of A union C1 plus probability of A union C2 all the way through probability of A union C sub k, since A intersection C sub I events are pairwise mutually exclusive. We now define the total probability of an event as follows. If C1 through C sub k represents a partition of sample space A, S, and A is an arbitrary event, then the total probability of event A is given by probability of A is probability of C1 multiplied by probability of A given C1 plus probability of C2 multiplied by probability of A given C2 through probability of C sub k multiplied by probability of A given C sub k. This total probability law is very useful to estimate indirectly probability of an event A. We now formally introduce Bayes' theorem and is based on total probability law. The theorem is stated as follows. If C1, C2 through C sub k constitute a partition of the sample space and A is an arbitrary event on S, then for I 1 through k, probability of C sub I given event A has happened is given by probability of C sub I multiplied by probability of A given C sub I divided by the summation, as explained in the numerical example. So if you go back to the previous example of 3 suppliers supplying the same parts to an OEM, each supplier has a different defect rate as well as different percentage of volume supplied. The portion of the sample space corresponds to each supplier. Let event A denotes the item is defective, and C sub I be the event that the item comes from facility I. Suppose you're interested to find out probability of C2 given A, that the defective item is from supplier 2. Then probability, according to Bayes' theorem, probability of C2 given A equals this expression, and numerically the value comes out to be 0.5, which we estimated earlier without using formally Bayes' theorem. So conditional probability is defined along with examples in this module. The concepts of independence of events, partitions of sample space, total probability, and Bayes' theorems are discussed in this module.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.